Hello everyone. In this video, I'm going to present my project, a Micromouse maze simulator built in Python using Streamlit. This project simulates a Micromouse robot that can move inside a competition-style maze, first by exploiting using Q-learning algorithm, and then by solving it using A algorithm to follow the shortest path to target. Okay, this micromaze competition are about small autonomous robot that must solve a maze as fast as possible. But in real competitions, the robot does not know the maze at the beginning. So the robot normally starts with exploration phase. What it means that the robot moves, discover and the maze and learn where it can go. And then for the second phase is the exploration speedrun phase. After collecting enough information, it computes the best route and runs the maze using the shortest path. So my project reproduces exactly this idea in a visual simulator. The maze is represented by 60 by 60 grid, which is standard Micromouse size. So the robot starts at 0.15 coordinate, bottom left corner, and the goal is in the center, which is changing the symmetries 2 by 2 block, the four cells. So the robot succeeds if it reaches any one of these four center cells. For the interface, we have four buttons. For the first button, which is generate random maze, this generates a new maze automatically, as it says in the title. The maze is displayed in a clean black and white shape with the thick block walls and clear boundaries like official Micromouse maze. For the second button is explore using Q-learning algorithms. You start the exploration phase and the robot starts moving automatically and tries to find the goal while learning how to move better. And for the third button, solve using the algorithm, this restart robot at the start, which means when the robot finally reach one of these cells, it go back to the start and then find the nearest road to take to reach one of the cells. And for the last button, which is reset, simple. It reset robot and clearing values while keeping them in the same maze, so we can test it again. First, we're gonna run a quick check to see if it actually works. I'm gonna run a quick test. The first thing first, we're gonna press the first button, which generate random maze. As you see, it generated us a new maze, and then we press the second button to explore the maze. As you see, our robot run and discover the map to see which is the quickest to find the goal. You see, our robot still discover the map. So we wait, I think it's gonna take a little bit of time until it reaches the goal, I think. Yeah. So yeah, I think it reaches, it stops. Reaches goals is true right now. Statue is exploring. Okay, so we're gonna press the third button, which is solve. She's gonna solve the shortest road possible, which is this one. This is the shortest road that our robot found. Mm, okay, wait. The goal says true, which means that our robot reached the goal. Process is kinda late. Okay, the goal, so it's true. And then if you want to reset the process again, gonna just press reset, as you see. Okay, now I think we're gonna pass for the code to look how our project run in the background. This is our code. which is NumPy. Usually use these three libraries: time, random, heap, queue. And then from typing, we import the dictionary, list, optional, tuple, etc. And the usual libraries: NumPy, Streamlit, Matplotlib, Pyplot. This is the libraries we're gonna need. And then we'll start by okay, now let's talk about how the maze is generated. The maze is created using a classical algorithm called randomized depth first search, call it the backtracking maze generation algorithm. The concept of this algorithm is like this. We start with a grid where every cell has walls for all four sides. Choose a starting cell and mark it visited. Then we repeatedly move to a random unvisited neighbor, removing the wall between them. If a cell has no unvisited neighbors, we backtrack it. This is what is called a perfect maze, meaning where every cell is reachable and there is exactly one unique path between any two cells. So the maze is always solvable and looks very similar to Micromouse competition layouts. For the robot exploration, we use Q-learning. I'm not gonna explain each line of this code. We're gonna just explain the whole concept of how our project works. In this video, I'm not gonna explain any line of code. I'm gonna just explain the whole part, the whole uh, project process. Now, the exploration phase using powered by Q-learning algorithm, which is reinforcement learning algorithm. In Q-learning, the robot learns a table called Q table. The state means that the state is the robot position in the grid x point u. The actions are the four movement: north, east, south, or east. So the Q table stores value like Q states and action. The idea is like become large. It means from this position, taking this action is a good idea. And so on, so on, so on. So for the kernel update, after each move, the Q table is updated using the reward, which is like the concept of the reinforcement learning. If you did this correct, you get a reward. If you do it right, you don't get nothing. You don't get a reward, of course. So, and then the estimated future best values from the next state. So over many steps, the robot improves its decision making in the simulation during exploration. You can see the blue trail showing there are the robot during the exploration. You can see the blue. This makes the learning behavior easy to understand visually. That's why I added the blue pad. And then for the final, stay here. For the shortest path for neighbors, after exploration, we want the robot to do a clean speed run using the best path possible. This is why I added a algorithm pathfinder for the solve phase. It works like this. Each cell is a node, and then moving to a neighbor cell cost one step. Also use a heuristic to estimate the distance to the goal. For the simulation, the heuristic is the Manhattan distance, which is another explanation in math. I'm not gonna go to the details right now. So I'm gonna just explain why this algorithm is good here. So it's widely used in robotic because it finds the optimal shortest path. That's one. The second is it is relatively fast. As you saw in our project, the robot was moving so fast, and it can be extended later to include extra cost to our dynamic obstacle. When we press solve, the simulator resets the robot to the start. I mean, it goes back to the start, computes the shortest path to the center, and then it draws that path in orange, and then animates the robot following it step by step. That's for now what it does. The project structure, what's inside the code. In the code, everything is in a single file, which calls app1py, but logically it's separated into models. Uh, as you see here, we have a shortest path, the kernel exploration, and then we have drawing, which draws us the map. And then, of course, there's others like visualization, the model, streamlit interface, etc., etc. And this is all our code. We have the main loop here that runs per click, animates inside one run. Uh, why this project is valuable for me and for you too? Because it combines two important approaches. We have reinforcement learning and the classical planning, which is A. That's exactly the logic behind many real autonomous robot system. It uses learning and exploration to understand the environment, then compute the best path and execute it. Also because it is built in Streamlit, which I used in the previous videos to build other projects. It becomes very easy to test different means and quickly visualize the result. So this is my Micromouse simulator project. A clean black and white maze generator, kernel exploration until reaching the goal, and a shortest path solving for the final run. Thank you for watching and see you next time.